Welcome back to yaymath.org and Yaymath in Studio. I am in the YouTube studios in sunny Los Angeles, California. My name is Robert Adout, and today we're going to be talking about weighted averages. My friend Zack was behind the camera now. I said the next videos, I got to dig deep for it. He said, why? I said, it's word problems. And like you felt the air come out of his gut, like, oh, like that. And yeah, dude, Zack, you're not alone. A lot of people feel that way. And my job today on your behalf here is to set the stage. So first we understand the problem, and then once we fully understand problems, then we'll try to give you some solving tools, okay? But I want you to think of it like an actual person, all right? Don't just solve blindly. Let's figure out what the problems are asking, and then we'll give you some tools and some surefire strategies to solve. All right, let's do this. Yay math. Here we go. So imagine, let's say I'm a juice company, and I have 40 gallons of fruit punch containing 15% fruit juice. So let's just pause there. So I have this like container, you know, let's just make it like a simple, something simple like this. All right, so this is 40 gallons, right? And I have it filled to the top, all right? And then within this mix, you could say, is like, let's say the full thing is full, like there, like all the way, filled to the top, all the way. And then within it though is 15% actual juice, all right? So it's like 15% juice. The rest might be water or filler or sugar or color or things like that, okay? But there's actual 15% fruit juice in this 40-gallon mixture, okay? How many gallons of 40% juice, so like a higher concentrate of juice, should we add to make my fruit punch contain 20% juice? Interesting, so this juice amount will actually go up. So what we need to do is we need to increase the size of the container, that's for sure. So let's say we still have 40 gallons, because if it's completely full to the top, then we can't really add anything. So notice how I'm just adjusting as I go, you know? There's no problem in that. It's a discovery along the way. It's a journey, right? Celebrate that with me. Celebrate the journey of discovery. And it's going to work out there. So we still have 40 gallons in this larger container. And I want to start to add 40% juice. So like this new juice coming in. Right? So dumping it in there. And that's like 40%. So you see it's more concentrated than the 15%. And so over time, the percentage of juice will go up. It'll go up to like 16% overall juice in the container, 17% overall juice in the container, 18, 19, and our goal is 20% juice. All right. So I hope that helped you understand the problem that we're trying to create a thicker juice content. So how do we do that? Okay. What we need to do is we need to create some sort of ratio. Okay. So you could say like, the ratio essentially is the amount of juice relative to the total punch, okay? So let's try that. Let's say like, let me move this over here. So 40% is going in. So use that space wisely for us, 40%. So let's say we have total, let's go, total juice over total punch. Okay? So we have this little ratio going. When I work with students on this, and they say, not the juice problem, this is what they mean. Not the juice problem. But really, like let's really try it together. Let's try it, okay? So we have first what kind of juice? We have the 15% brand, all right? So let's do the 15% is right here. We have the 15% juice problem. 15% punch, you could say. Okay. Then we add to it, we add the 40% variety. Make that pink. 40% punch. We have that kind. And we have our mix total. Okay, so let's see it. With regards to the 15% punch, I know how much punch we have, 40. I have 40 gallons of the fruit punch, so we'll put 40 down. Within this 40, how much juice is that? How much juice? Well, I know it's 15% of this. So what I can do is I could say 0.15, which is 15%, times 40. Because of the 40, 15% of those 40 gallons is actual juice, right? And if I wanted to multiply through, I could do a distributive style, 10% of 40 and 5% of 40. 10% of 40 is 4. 5% of 40 is half of that. Half of 4 is 2. So 4 and 2 together, that makes 6. So 6 is 15% of 40. So of the 40 gallons, 6 gallons is juice. 6 gal. Out of the 40. Okay, gallons. So far, so good. Then we put in the 40% punch. How many gallons of 40% punch, 40% juice in punch, you could say, should I add to make my thing a different concentration, okay? How many gallons? We don't know. We don't know how many gallons of this punch to add. However, we do know how much of it is juice. We know that in this X amount of total punch that we're adding in, 40% of this, 40% of the gallons is actual juice. So just like we did over here, we're going to do 40%, 0.4 of X. All right, see that? Whatever this is 40%. But we don't know what it is, but that's okay. You can still multiply them, okay? So we had some original amount and we added. We had some original amount and we added. So the total liquid in this container is 40 plus X. That's the total liquid. And the total juice is right here. We started with 6 gallons of juice and we added, it's weird, but it's true, 0.4x gallons of juice. So we added 6 to this too. That's the total amount of juice, pure juice. And this is the total amount of liquid. So this is the ratio of the new mix. This ratio of juice to punch must be 20%. All right, and now we can create an equation, right? This is the part where it pays off. So let's do our ratio. Juice to punch equals 20%. 20% means over 100. It's gotten real. I'm gonna take my shoes off. Let's do this. It's getting real now. Here we go. I'm gonna take this on comfortably. It's like we're in the family room now. Let's do this. This is a home environment. Here we go. Let's do it. 20 over 100. Good. So we could simplify this. It's always good. Cross multiplication will help. But before we cross multiply, what we can do is we can simplify. 20 and 100 have a common factor of 20, and that's 1 over 5, right? So now we can cross multiply. 5 hits this. Let's write it all out. 5 times 6 plus 0.4x equals 1 times 40 plus x. Good, there we go. And now we distribute and solve, solving for x. 5 times 6, 30, plus 0.4 times 5 is 2. It's 5 times 4, which is 20, and then move the decimal. So that's 2x equals 40 plus x. All right, we're moving stuff around. I'm going to solve for x. Minus x both sides, minus x both sides. There it is. I'll bring the 30 over. Here, I need some of that juice right now. Here we go, boom. So now we got 2x minus x is x equals, there it is, 10. What is x measuring? The total amount of punch that we added, the 40%. So this is, we have to add. It's kind of fascinating. If you had 40 gallons at 15% juice concentrate, if you added 10 gallons of 40% concentrate, the end result would be 20% concentrate. All right. So that's the juice problem. Looking at it together, wow, it's hardcore. I really don't blame people for having a little hesitation for doing this stuff, but I'm just trying to introduce it in ways to remove some of that hesitation. Next problem. Two trains are heading in opposite directions. Let's draw them. Let's draw the two trains. There we go. Going. It's a short train. It's all good. And then we got at least they sound the same. Heading in opposite directions. One is going 42 miles per hour. Put it. One is going 52 miles per hour. Faster. Okay. How long will it take for them to be 423 miles apart from each other? Okay. You could reason this out, or we could create an equation. The way to create the equation, a really good method for a lot of word problems is creating a table or creating a chart here, just like we did in the last problem. With distance and time and rate problems, we have the ironclad physics formula, which is, let's put it down here, maybe in like perps. Actually, I'll put it in black. The formula goes rate times time equals distance, right? We talked about not taking formulas wholesale. We don't want to lead with the formula. Never start with the formula outright. You know, it's not inspiring. Only time you should have formula first is, I feel like, I don't know, feeding a baby. That way, eat that. But otherwise, don't live with formulas. Rate times time equals distance. You know it. I know it. If you're going 60 miles per hour for 2 hours, right? Immediately you know, oh, 60 miles per hour, hour one, hour two. I went 2 of these 60s is 120 miles. Bada bing, bada boom, you just did that. Rate times time equals distance. So that's why we're employing this formula. All right? Rate times time equals distance. So let's do it. We have the first train and the second train. Now pick a different color. Okay, let's fill out what we know. Well, we know the rate of the first train, 42 miles per hour. Boom. We know the rate of the second train, 52 miles per hour. The time the first train goes, the time the second train goes. Check it out. How long will it take for them? Meaning, how much time? Meaning, we don't know this. The question is, are they going the same amount of time? Think it in your mind, like they leave. Stop. Yes, they are going the same amount of time. So they're going time and time. This will probably be measured in hours, right? Because we're miles per hour. So this will be some matter of hours. Follow the formula. Rate times time is distance. Rate times time is 42t. There it is. 52t. Okay. So it turns out that the first train went 42t miles. That's a distance. That's a distance. It's a little strange to say, oh, how far did the train go? 42t. But it's really true because if you don't know t, you just have to say 42t. So this is a distance. This distance is measured in miles. So in fact, we could say it went la 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 la. This is, well, that was the 52t. So we'll go over here, la 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 la, like I was saying, la 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 la, 42t. That's the distance that the first train went. 52t. That's the distance that the second train went. And it turns out that they should be 423 miles apart. This length between them, like at the ends between them, is 423. So would it make sense to you to add these two distances, one going this way, one going that way, and together they make 423? Because that's what we need to do. So I hope it does make sense. Let's do it. Here we go. 42t, I'll write it out. 42t plus 52t equals 423. Bravo, there it is. That's the equation. These two distances. Always make sure you create an equation that has the same units. This is a distance, this is a distance, this is a distance, right? Never create an equation with distance and rate in it, for example, or distance and time in it. You want to have an equation with one unit. Add them up. This is, what is that? 94t equals 423. Divide both sides by 94. Divide both sides by 94. Good. Yeah, 94. Good. And let's get the calc going. Drink. Unlock that. Here we go. 423 divided by 94. 4.5. Said emphatically. And what are we measuring? 4.5. What was T measuring? T's measuring time. Time's measured in units of hours. So it's important to articulate it in a full sentence. If one train is going in one direction at 42 miles an hour, the other train going at 52 miles an hour, after 4.5 hours, they would be 423 miles apart. All right. Something satisfying about it. 2 down, 2 to go. Good. All right, next problem. So suppose I ride my bike for 5 miles and it takes 40 minutes to get to my destination. And then it takes me 30 minutes to get back. So a couple things. First of all, let's see how that makes sense. If you've ever ridden a bike before, if it takes you 40 minutes to get somewhere and 30 minutes to get back, most likely it's not because I'm like chugging it hard. It's probably because on the way there it's uphill, took me longer, and on the way back it's downhill, right? So it took me less time. It's still 5 miles though, keep that in mind. So let's say I'm here, I start here, go up, this is the destination. It took me, let's go there in green. This was 40 mins, 5 miles. And then it took me 30 minutes to get back. Kind of interesting. Back 30 minutes. All right, so that's the first thing to keep in mind. Sometimes the time it takes to go there and back are different based on hills in this case. Common sense. Or it's a common sense assumption, right? I didn't ask a question yet. I did that on purpose. What could I ask? What could I ask? There's a huge sense of empowerment in figuring out what you could ask, because it's like, then you need to know, like, well, what am I missing? Let's see, I could ask, like, should I ask the total time? Not really, no, because I know it's 40 minutes there and 30 minutes back. 70 minutes round trip, so I already know the total time. I don't need to ask that. Total distance traveled. I know that as well. 5 miles there, 5 miles that back. That's 10 miles round trip. So what could I ask? A hint, if you don't have that question in your mind, has to do with my speed. Okay? So I could possibly calculate my speed there, and I could possibly calculate my speed back. So we're going to do that. I don't know my speed there, and I don't know my speed back. More importantly, since this is about averages, is what my average speed was. And this is where it gets really challenging, what's my average speed? Because I'll tell you right now, it's not the average of the two speeds. It's not the average of the two speeds, which is kind of so fascinating when I was learning this stuff and when I was teaching it. Like if you think of it, let's just say hypothetically, I was going 10 miles per hour there, and then I was going faster back, right? Because it was going downhill, vroom, took me less time. And then let's say it took me 20 miles an hour back. The temptation is to average these, you know, to say, yo, oh, perfect. 10 miles an hour there. I was faster back, 20 miles an hour back. So the average is the middle of that. That's 15 miles per hour. This is wrong because I was riding for more time here. See what I mean? Like I went for more time slower. So in a sense, this is going to be weighted more. This is going to be weighted more for longer. I was chugging, chugging for 10 minutes more. So on average, my speed will actually be lower compared to these two. So it wouldn't necessarily be 15, maybe like 14, 13, something like that. All right? So that's what I'm going to show you how this works. You have to sort of factor in the fact that we're riding for longer in one direction. So it's not a straight traditional average. Okay? I hope that helped. So let's go ahead and do our distance equals rate times time process, starting with rate times time equals D. All right, so we have there. I should probably say there to you to calm you down. There, there, and back. You'll be fine. I got your back. There, got your back. All right? So, let's figure out what we know. The good thing about a chart is that you can just fill in one piece at a time. Don't really have the rate, but I do have the time. What I'd like to do is I'd like to put the time into hours, even though it says 40 minutes, because then we can make our speed like miles per hour. So what we need to do is we need to convert minutes into hours. 40 minutes into hours. So 40 minutes is more than half an hour. What you could do, I'll pick green this time, is you could say it's like 40 over 60. That's the fraction of an hour. 40 minutes out of 60 minutes is 2/3. 2/3 of an hour there is 40 minutes. 30 minutes on the way back. It's a little more straightforward. 30 minutes, maybe you know, is half an hour. So I could put 1/2 here. Let's box it so we could see it. Okay. What else do we know? Boom. I know distance. 5 miles there. Did our destination magically become farther away when it's time to go back home? No. 5. All right. I don't know my rate there. I don't know my rate back. But let's get it. Let's get it. Let's call it, you know, like you could say R1. You could say R2. You know, you could do these things for our information. All right, let's follow the formula just like we did the last problem. Rate times time equals distance. So here we go. That would mean 2/3 times R1 equals 5. And then we have 1/2 times R2 equals 5. All right, solving for R, multiply by reciprocal. Let's go ahead and do that in red here. Times 3/2 times 3/2. Going. That's R equals 15/2. 15/2. So that first rate is 7.5. It's 15/2. All right, let's put that down. 7.5 miles per hour on the way there. It looks like on the way back we're going to go faster because we're going like downhill. Takes us less time. Lo and behold, we hit that. R2 equals 10. Yeah, we're going faster on the way back. So it's 10 miles per hour on the way back. Okay, so again, we can't just average these. If I want my average speed, I can't average them. This is what I need to do. If we need to weight them differently, they need to have sort of like different power. And if they're going to have different power in our equation, we have to just add them up as they are. Here's what I mean. If r times t equals d, observe, here's what I mean, r t equals d. Now, since I want a speed, let's get r by itself by dividing by time. So essentially, the rate will be the total distance and the total time it took to get there. The total distance and the total time it took to get there. Okay, so let's try it. The total distance overall, okay, was 5 there, 5 back. That is 10 over. The total time collectively is 2/3 of an hour plus 1/2 of an hour. 2/3 plus 1/2. Now you see we're creating a ratio of totals, okay? So now each of these are weighted differently. Like the 2/3 and the 1/2 are now equally, well not equally, but like they each have some sort of influence in the equation instead of simply averaging something that took different time to do. So here we go, 10 over. Common denominator would be 6 in this case. So this would be times 2 top and bottom. This would be times 3 top and bottom. That's what we got. 4 over 6 plus 3 over 6. And that's 7 over 6. All right, good job. And so what we can do in this case is this is the same as 10 divided by 7 over 6. Actually, I like the vertical fraction. You'll see what I mean. 10 divided by 7 over 6, which is the same as 10 times the reciprocal 6 over 7. So dividing by a fraction is the same as multiplying by its reciprocal. Multiply across, we get 60 over 7. Now that's not really meaningful until we get it in speed, which is measured in miles per hour. So let's get the handy dandy personal calculator. Unlock it, boom. We got 60 over 7. 8.6 rounded, 8.57 I got, but 8.6. And now let's confirm if this is a rate, an average speed, that's miles per hour. And we have to look and see 8.6 is indeed closer to the 7.5. So that's one of the reasons we got 8.6 is between these two. My speed there is 7.5. That's like 1.1 away. 1.1 away. This is 1.4 away. So you can see my speed was like slower because I was doing this for a longer amount of time. I was doing this for 40 minutes, where I was doing this for only 30 minutes. So that slow time it took to get there had more of an influence, had more of a weight on my average speed. So that's why it's 8.6 miles per hour. Nice work. That was a doozy. A doozy. And we doozed it. I don't know what that means. Okay, last one of this particular lesson. Okay, a boat travels 36 miles in 1.5 hours and 15 miles in 45 minutes. What was the average speed? Okay, so this is similar to the last problem. We have a little bit of curveball here. We see one time is given in hours and the other time is given in minutes. So we should sort of make them both into hours and we can get that average speed. So here we go. So rate times time equals distance. Here we go. All right. So we could say first leg, second leg of the journey. Okay, what do we know? What do we know? We know the time in the first leg is 1.5. It's kind of fun. You just fill in what you know, and then it'll open up. We know the time, over here, 45 minutes. I'm going to turn that into hours, just like we did last time. 45 over 60 minutes. Maybe you know that 45 is 3/4 of an hour, 45 minutes. Or divide top and bottom by 15, and you get 3/4. In fact, if we want to go consistency for decimals, 3/4 is 0.75. So let's just do that one, 0.75. Let's leave it at that one. Okay, good. Notice we're just figuring it out as we go, okay? So we don't know how fast it was going the first way. We do know the distance. Do we know the distance? Yes, we know 36 miles. And we know 15 miles. Okay, and again, this was R1 and R2. Last time we solved for these rates. Maybe you noticed that we didn't need to. It's nice to, and you saw how, by multiplying R times 1.5 equals 36 and so forth, solving for R. But what we can do instead is just go straight for the average speed, now that we have our sea legs, you know? So let's do this. So the rate is the overall distance over the overall time. Total distance, 36 plus 15. Total time, 1.5 plus 1 or 0.75. That's all it is. Look at that. It's so cool. Your total distance and the total time it took, that'll give you your overall rate, your average speed. That's what it'll give you. All right, rocking and rolling. These two together make 40 plus 11, 51. These two together make 1.5 plus 0.75. This is 2.25. All right. Set it up, set it up, set it up today, set it up today. 51 divided by 2.25. 22.6 repeating. 22.6 repeating. And that is a rate, and that is in miles per hour. Okay, so it turns out that if I travel 36 miles in 1.5 hours, then it takes me 3/4 of an hour to go 15 miles. Overall, the average is 22.6 miles per hour was my speed. All right, good job. I hope you like this. You know, I sort of got into the flow of it. I wanted to do that so you got into that flow as well. So thank you. Thanks for committing to this process with me. Yay, math!